trust your theory. So you think there should be 2 peaks. So when you see a peak, you say, no, that's not right. When I see there's only 1 peak, you don't know. According to our model, you have 2 peaks.
Yeah.
So then you say there's 2 peaks because of the resolution, so we cannot get it. Right?
It's not fair statement.
I think it's a different way of one can actually try to add another peak, but it doesn't matter.
So anyway, if you assume there's another thing, that other thing has very little significance.
Yes.
Because it's only 1 sigma away from this step. That thing that you see as jumping up, it's only 1 sigma.
So this error bar is here, right? So if you're adding 1 ping, it's 1 sigma.
Making another assumption to fit another particle, whatever, is very low significance.
But it can be done by somebody. A crazy idea can put in, but
this is a very commonly used in particle physics.
But not in solid state.
I know it's not. Maybe probably not. I mean, for example, discovery of the epsilon 3 peak. There's 3 epsilon prime, double prime. Okay, the first data come out. Very hard to see. Okay, there's 3 peaks. The 2 maybe. Okay, but then based on the experimental resolution, then you can fit with either 2 or 3. Then it come out. Okay, of course later will be verified by much better. The much precise experiment. Same thing here. For discovery, this question is the
I mean,
how much you know.
I have to say that the resolution, the data point is not big enough to say that it's exactly the case. You might have other mechanism which give you something else.
It's all stated with statistical significance, right? Because here you can only claim, maybe up to 3 sigma, but not more.
Actually, this one is slightly lower. This thing is lower. This thing is higher.
Can I add to that?
Yeah.
You can fit the data with just 1 peak. The highest peak.
Probably BS.
The BS.
Will be shifted.
Then you can fit the data. I mean, this is practically what happens here. Then you can fit the data without any peak. That's the profile likelihood method, and you divide the 2 likelihoods. Or you can fit the data with a small peak or with 2 peaks. If you do all these combinations, you will see
actually,
that
this is exactly the scan means, right? So here is like no peak at all. This one is totally floated, and along this line is only 1 peak. On this line is only 1 peak. So when you compare the so-called likelihood value, we can climb up to that kind of scenario. That's why we need to provide this kind of scan to tell people the different assumptions. Actually, this alone is I didn't spend too much time on this, but in principle, this is the idea. Just Cesar just mentioned. It's a single peak idea.
So the fit is quite free. I mean, there is a lot of freedom in this function that he shows, and at the end, this is a consistent result with the significance that comes out.
Well, also there's 155 parameters in the phase. So well, I was told this is just the second complicated fit. Only slightly worse. I mean, better than Higgs result. Higgs has more parameters, but this guy is second most complicated fit so far.
Okay, further questions? Okay, priority for outside of HEP experiment. Okay.
I'm not outside of HEP.
Experiment. And he said too much already. So.
When you have more integrated luminosity, will Atlas be in the game, or do they just have lower resolution for momentum?
Well, I think really the issue is that the Atlas need a better tracking resolution to separate these 2 peaks. Basically, Atlas has no resolution to separate these 2. CMS is just barely separating, and Atlas is just a big lump. So.
Is it resolution for muon tracks?
Yeah.
That's because of the magnetic field?
Yeah, that's exactly.
Or smaller inner detector with weaker magnetic field, what can you do?
And TRT.
Fewer tracking planes.
And TRT.
Okay, but Sanders, you had another question?
I just want to congratulate him because the CMS data are extremely clear. For me, the CMS result is so he must have done something right. It's really impressive. No, it's really impressive.
Okay, but then I have a question. Can you go to the outlook projection?
Okay, I jumped to the end. Just as I said, it's the Christmas, right?
There are 2 questions. One thing is 2018 with question mark, but you use standard model, right?
Yes.
So how many sigmas, this question is a little bit complicated. How many sigmas will reach with the current central value? But then
Actually, I did, but it's not in the official reference. I have a number.
not-
I have a
not
number I can show you privately if you want.
Okay.
Yeah.
Not official meaning you cannot even discuss this?
No, I think I can say it will be above 4 sigma at the 300.
With this current central value?
Yeah.
Oh, you need 300 for that?
Yeah, because the current 3 sigma is combined of 2 data sets.
Oh, I see.
So we will downgrade to 1 sigma or 2 sigma, right? 2 to yeah.
Right, so I'm concerned with when will be that announcement, assuming the current central value?
Yeah, well, I think will be before this actually. Well, become like a stable, like a 4 sigma, 5 sigma. But the issue is the cinematics is I didn't put the full cinematic yet, so I think it's a problem.
So the other question is that here there's no mention of. Oh, okay, you do have it.
Yeah.
So assuming the current deviation is slightly below, what is the time we'll reach significance?
Okay, this is a tougher thing. Even at the the error bar will be stopped at like a 10 to 13% error bar. So we are now just like 20%, 30% lower, 30% lower. So even at the end of the day, it's only like a 2 sigma below the model.
End of the day meaning 3,000?
Yeah, 3,000.
So pessimistic.
Yeah,
It is.
but this is something
In
we can
case
try.
people didn't understand my question,
Yeah.
these are the questions about indication for new physics.
Yeah.
Because currently one is low, one is high. So if the trend will stay.
Yeah.
Okay. Any further questions? Finally, you did not explain beautifully strange.
Okay. Oh, okay. I didn't say at the beginning. I should say at the beginning. Okay. There's a B and B quark and strange quark combined. So
Beauty
big
is strange.
strange.
Decaying to dimuons.
Yeah, I didn't. I should say at the beginning. Sorry.
Oh, there is a.
Or a strange bottom.
Yeah. It's a strange part. That's right.
Related process B to K mu.
Yeah.
Can you measure that also like LHC did?
No. Answer is no.
Because
It's much difficult for us.
that also has a deficit relative to the standard models.
Yep.
We can measure it to a very good degree if we donate all our resources to that, and that cannot happen.
Yeah.
This is a big experiment with multi-purposes.
Yeah. Basically, we'll eat. If we want to get the same performance at GCP, we'll probably want to eat up 50% of the total trigger bandwidth, and we'll be killed by Higgs people and SUSY people. We'll pick a big knife, like want the bandwidth.
Well, okay. Just saying to select those events, you need to spend a lot of effort, but that equivalent amount of effort is spent elsewhere. I hope you understand that. Okay. Okay. So. No other questions?
I still wanted that point.
Yeah. Okay.
Join the experiment.
Yeah, join us. And you can do the fit, whatever you like.
If the point
Okay,
was
there's
it will be cheap.
There's a younger person question which I'll allow.
I have
That's
a
right.
technical question.
Okay.
Too good.
You just mentioned about the different starting point will cause the different result, right? I want to know how big.
You mean difference in terms of what?
The starting point.
Yeah. Well, the result is like well. Also I say the result in difference, but the difference is like one ppm level.
Okay.
Because we are fitting there are so many events, so the total sum likelihood value is huge. Even if you take a log, it's like 10 to 7, 10 to 8. So we get 1 or 2 different by 1 or 2 on a big number like 10 to 8, 10 to 9. But we want to make very sure, even up to 4-point limitation, that we are concerned with to implementation of features. Yeah.
The next question is.
Okay, I think if it's a technical question, we do it offline.
Yeah.
Okay. So let's thank Jack again.